In today's video, we're going to be talking about free fall. After watching this video, you should be able to understand what free fall is and then be able to use some free fall formulas. So let's get right to it. What the heck is free fall in the first place? Basically, the definition of free fall is any object that is being acted upon only by the force of gravity. Nothing else is pushing on it, pulling on it, doing anything to it. It's just being acted upon by the force of gravity. So an example would be like if you ever have ever thought about walking up to the top of the Empire State Building and dropping a penny off the top of the Empire State Building. Very illegal, but if you ever did do that, basically the only force acting on that penny would be the force of gravity. There are some assumptions that we make in dealing with free fall, and one of those assumptions is that free-falling objects do not encounter air resistance. Okay, because obviously, clearly, if you drop a napkin from the top of the Empire State Building, you know it's going to encounter some air resistance. But for our purposes, we're going to assume air resistance is, for the most part, negligible, and we're not going to worry about it. So free-falling objects do not encounter air resistance. All objects on Earth anyway, all free-falling objects on Earth, accelerate down towards the Earth at a rate of 9.8 meters per second squared. This is a number that is worth memorizing. It will come up over and over and over again. So 9.8 meters per second squared, that is what the acceleration is of all objects on Earth. Okay? And it's actually such an important number that in physics it's been given the symbol G. Okay, so if I ever refer to something like G, if I ask, you know, like what is G on Earth, it would be 9.8 meters per second squared. Now this is not true on like the moon or Mars or anything like that. Those planets all have different G's. But on Earth, which is where we'll be doing most of our physics, I would say, you should know that G is 9.8 meters per second squared. So we've been doing some ticker tape diagrams, at least we did a few lessons ago, and if I were to do a ticker tape diagram of a free-falling object, here you can see this guy is standing on top of a cliff and he's dropping some object. And this is basically a snapshot of the object at various points in its fall. And basically the only force acting on this object is gravity. Okay, and so this object is accelerating downwards with a speed of 9.8 meters per second squared. And you'll notice it starts off very slow, right? Like the distance from here to there is not very much. But then as time progresses, it's accelerating more, and so the distance gets bigger and bigger and bigger. And you'll notice that basically it's moving faster and faster and faster. This is true if you were to jump out of a plane. The first, second or two after you jump out of the plane, you'd be going fast, but you wouldn't be going that fast. Whereas like 20 seconds after falling out of the plane, which I don't even know if that's how long it takes for you to finally hit the ground, you would be going at a pretty fast rate. Okay, your velocity would be much higher than when you first initially jumped out of a plane. So if we were to make a graph of free fall, which is funny because we've been just talking about graphing, a curved line on a position versus time graph, signifies basically an accelerated motion or a change in the velocity. Okay, whereas a diagonal line indicates an acceleration in a velocity versus time graph. Okay, so this slide might almost be a little confusing because there's so much stuff going on it. But on the left, notice on the left-hand side, I have a position versus time graph. And when you've got this curved line, basically that's indicating that the object is moving, and because it's curved, it's actually either, in this case anyway, because it's curved, it's actually speeding up, it's accelerating, it's getting faster. So it starts off kind of slow, and then as the slope gets steeper, it begins to accelerate faster and faster. This graph on the right is a velocity versus time graph, and remember, if it's a straight line and has some slope to it, then it means some acceleration is occurring. Okay, and it looks like a constant acceleration, and in this case, the acceleration is 9.8 meters per second squared, is what's going on. Okay, so we can represent this motion by a graph. So we looked at a ticker tape diagram. Now we've looked at it as a graph. These are some formulas that you should be familiar with. The formula for determining the velocity of a falling object after a certain amount of time is basically this guy right here, where V sub f stands for velocity final, or final velocity, however you want to say it, and then G is 9.8 meters per second squared. That's the acceleration due to gravity. And t is time. Okay, how long did it get to be able to accelerate at this rate? Okay. Another formula that turns out to be handy is this formula here to determine the distance fallen after a time of t seconds. And so let's say I'm wondering how far would I have fallen if I jumped out of a plane and I let myself fall for 3 seconds. How far would I get? Well, this formula could actually help me solve that and figure that out. So it is 1/2 or 0.5, whichever you prefer, times g times time squared. Okay, and I'm going to do some examples of this in the next slide. Okay, so our first example says calculate the velocity of a free-falling object after 6 seconds and 8 seconds. Okay, so I'm going to use this equation, v final, because that's what we're looking for is the velocity, the final velocity, equals g times t. Okay, where g is 9.8 and t is whatever the time is. So we're looking at 6 seconds, and in another case we're looking at 8 seconds. So basically I'm going to take the 6-second one first, and I'm going to take 9.8 times 6 seconds. And if you throw that in your calculator, I get a speed of about 58.8 meters per second. Okay, 58.8 meters per second. Pretty dang fast, okay, but that kind of makes sense. If you're accelerating at 9.8 meters per second squared, you're going to get up to a quick velocity, in no time flat. At 8 seconds, I would just do the same exact procedure. I'd take 9.8 times my time, which is now 8 seconds. And if I do that math, I get 78.4 meters per second. Okay, so clearly even faster. So 2 seconds later, I'm almost going, not almost, I'm like going 20 meters per second faster, just in 2 seconds change. Okay, so that's how you use the first formula. The second one, it says calculate the distance fallen by a free-falling object after 1 second and 2 seconds. So to do that, let's see here, we're going to use this formula. D equals 1/2 gt squared. Okay, so my first one is dealing with 1 second. So 1/2 or 0.5, whichever you prefer, times 9.8, which is the acceleration due to gravity, times 1 squared. And if you do that math, I get 4.9 meters would be my answer, 4.9 meters. For the second one, with 2 seconds, I would take 1/2 times 9.8, g still hasn't changed, times the time squared, so 2 squared. And if you do that math, I get 19.6 meters. Okay, and so these numbers are telling you how far you would have fallen after 1 second and after 2 seconds. And we could do 3 seconds if you want. I mean, just take that 2 out and plug in a 3 in its place. Okay, just some simple formulas that go along with this idea of free fall, which is basically an object that the only force acting upon it is gravity. And gravity pulls us down towards the Earth at a whopping acceleration of 9.8 meters per second squared. One relatively large misconception that students have with free-falling objects is that the more massive an object is, the more it's going to accelerate and it's going to hit the ground faster. Okay, so like a good example would be like, let's say I drop a brick, a 40-pound brick. It's one of the biggest bricks I've ever seen, and a penny. At the same time, I drop them from like the top of a ladder. Which one hits the ground first? And most people, I shouldn't say most, but I think a majority of people would say, oh, well, the brick hits the ground first. And that is a misconception. The more massive an object is actually has nothing to really do with how fast it accelerates to the ground. Everything on Earth accelerates down towards the ground at a rate of 9.8 meters per second squared. So a more massive object actually doesn't accelerate faster than a less massive object. Okay, so remember, free fall is only the only force acting on a free-falling object is the influence of gravity. So the mass of the object has actually nothing to do with the rate that it accelerates. Now, we all know, I think, if you take like a Kleenex and a penny and you drop them from the top of the ladder, the penny will hit the ground first and the Kleenex will hit the ground second. And you may say, well, why is that, Benny? Are you lying to me here? The reason is air resistance obviously does play a role in that. Okay, so the air resistance is going to hold the Kleenex up. It's going to slow it down a lot more than, say, the penny does. But I don't know if any of you guys have ever seen on the moon landings, where there's no atmosphere, so there's no air resistance, one of the astronauts dropped a hammer and a feather, and they both fell to the moon at the same rate. They both hit the ground at the same time because there's no air resistance to slow it down, and so they both accelerated down towards the ground at the same rate. That takes care of this video. I will see you guys next time.